to see how row operations and elementary matrices and matrix multiplication all fit together, let's actually work out an example. So here's a matrix A. Let's multiply this by elementary matrices to produce the reduced row echelon form of A. In other words, what I'm saying is, starting with this matrix A, let's come up with the appropriate elementary matrices so that multiplying all of them together like this is down to ER, produces the reduced row echelon form of A. Remember that to figure out what these elementary matrices are, we just need to think about what row operation we want to do, because these elementary matrices correspond to row operations. So what is the first row operation we would do? Maybe interchange the first and second rows, just so that we get a 1 in the upper left. So the effect that will have on the matrix is to give us 1, minus 3, minus 1, minus 2, 5, 1, minus 1, 1, 0. And the matrix that would make this happen, well, let's keep track of all the matrices down here, is the elementary matrix corresponding to interchanging the first two rows. And I'm going to put this over here. This is the first one that we're doing, so when we multiply it by A, it's sort of closest to A. And as we do more of them, they sort of stack up to the left. So I'm going to write the first one we do down here, just to keep them in order. So remember, to produce the elementary matrix that does this row operation, we do this row operation to the identity. So to imagine the identity, switch the first and second rows. That gives us 0, 1, 0, 1, 0, 0, 0, 0, 1. So this was our first elementary matrix. Okay, now the next row operation, I guess we would add to row 2, we would add 2 times row 1. And then immediately after that, we would, to row 3, we would add row 1. Okay, so that's going to give us 1 minus 3 minus 1, 0, minus 1, minus 1, and then 0, minus 2, 0. Okay, and what are the elementary matrices? Remember, the elementary matrices stack up leftwards in the order opposite that these are going rightwards. So we start with this one. So to add a multiple of a row to another row, it's 1s down the diagonal, and then you have one off-diagonal entry that corresponds to this coefficient. So we are adding twice row 1 to row 2, so that's going to be a 2 right here. And then we need an elementary matrix that adds row 1 to row 3, so 1's down the diagonal, and then a 1 right here. You'll see that the elementary matrices, most of their entries are 0, so just to save time, any entry that I don't write, assume it's 0, because it is. Okay, next I guess maybe we should multiply the second row by minus 1. So that's going to give us 1 minus 3 minus 1, 0, 1, 1, 0, minus 2, 0. Actually, why don't we do two things at once here? After we do this operation, let's also multiply row 3 by minus a half to make this a 1 here. Actually, let's make a positive a half. You'll see why in a second. Okay, so first let's write the elementary matrix for this operation. So we're scaling row 2, so the 2, 2 entry is going to be the constant we're scaling by, so that's minus 1. Everything else is 1's on the diagonal, 0's off the diagonal. Okay, and then to multiply row 3 by a half, we need a 1/2 down here. Okay, next, and that's going to make this a minus 1. Next operation, we'll add row 3, we will add row 2. Now you see why I wanted this to be a minus 1, so that this would be nice. So that gives us 1 minus 3 -1, 0, 1, 1, 0, 0, 1. Okay. Writing these elementary matrices takes a lot of space, but fortunately no single matrix is very complicated. So let's see. 1's down the diagonal when you're adding a row to another row. We're adding a higher row to a lower row, so 2, 3 right here. We need a 1. Okay, next we want to add to row 2. We're going to subtract row 3. And then immediately afterwards, right, we can zero out this element right here. Row 1, we can add row 3. So I'm going to continue. I'm out of room this way, so I'm going to continue here. I might run out of room altogether. We'll see. So this one is going to be, let's see, for this one, it's 1's down the diagonal. And now we're adding upwards, so we're going to have entries above the diagonal. And from row 2 to row 3, we need a -1 right here. And I'm going to start writing these smaller because I might run out of room. And then to add row 3 to row 1, we need a 1 right there. This is going to give us 1 minus 3, 0, 0, 1, 0, 0, 0, 1. Okay, and now there's only one operation left, so actually we are going to have room. The only operation left is to take row 1 and add 3 times row 2. And so this is 1's down the diagonal and then a 3 right here. Okay, so we did it. Multiplying this matrix on the left by this series of elementary matrices will produce the reduced row echelon form of the matrix A. And I guess I didn't write it, but the reduced row echelon form turns out to be the 3×3 identity here. All right, let's look at one other thing that this example tells us. Just as a follow-up question, let's write A as a product of elementary matrices. So what we have here is, so this is E1, 2, 3, 4, 5, 6, 7, 8, 9. So we had 9 elementary matrices, and by multiplying them all together times A, right, if you start with A and then do this row operation, then the next one, and so on, what we saw is you end up with the identity matrix, the identity of size 3. So that means if we then undo all of these row operations, starting with the 9th one and then working our way back to the first one, what we will have is, right, if we multiply, let's do this step by step. If we multiply on the left by a matrix that undoes the 9th operation, let's call that D9, then we would have to multiply by D9 over here, and then we have E8 multiplied down to E1 times A equals D9 times I3. And then we would do the same thing with the next operation. So multiply by whatever operation it is that undoes the 8th one. So I'll call that D8, and that would give us a D8 here. And so on. When we do all of this, right, we're undoing all of these E's essentially. What we get when we're done is A times D1 multiplied down to D9 times the identity matrix, which, right, multiplying by the identity doesn't change it. So what this will do for us is it will display A as a product of elementary matrices, right? This identity here is playing the role of the reduced row echelon form. So what we're doing here is explicitly writing A as its reduced row echelon form times a bunch of elementary matrices. So let's go ahead and do that. All we need to do is figure out what matrix it is that undoes each of these row operation matrices, these elementary matrices that we started with, and then put them in this order. Notice that they're in the opposite order as the elementary matrices, right? So first we need to write down D1, which is the operation that undoes E1. So how do you undo a row interchange? Well, you do the exact same row interchange again, right? The first row interchange would switch the rows, but then doing it again will switch them back to where they used to be. So D1 here is this, okay? And then second row operation, how do you undo adding the how do you undo adding twice the first row to the second row? Well, you subtract twice the first row from the second row, so a -2 there. 1's down the diagonal. And then for this one, how do you undo adding the first row to the third? You subtract the first row from the third. Okay, and then how do you undo multiplying the second row by -1? You multiply the second row by -1 again. Okay, and then how do you undo multiplying the third row by 1/2? You multiply the third row by 2. How do you undo adding the second row to the third row? You subtract the second row from the third row. Okay, and now we're going to have another row down here. And now we have to scroll back and forth to see what the heck we were doing. So next we subtracted the third row from the second row. So now to undo that, we would add the third row to the second row. Then we added the third row to the first row. To undo that, we would subtract the third row from the first row. And then last operation was adding 3 times the second row to the first row. So to undo that, we would subtract 3 times the first row. Sorry, subtract 3 times the second row from the first row. Did I get the sign right? Yeah. Okay, so this giant matrix product is the matrix A. Now I won't actually work out this product to observe that it is equal to A, but in fact it is. We know it has to be.